Hi guys, Dr. Musk back again. So in this video, we're going to be talking about one of the periodic properties of the atoms. We're going to be talking about atomic radius. So first, let's define that, all right? There's a simple definition, which is like, how big is this atom? Its radius is a measure of that atom's size. Now, we are not going to be able to calculate an atomic radius, but we should be able to tell with these periodic properties based on where that atom is on the periodic table, whether it's bigger or smaller to a first approximation than some other atom on the periodic table. So how can we tell? First of all, let's talk about what the periodic table tells us about this trend. A little bit. So on our periodic table, it turns out that atomic radius increases as we go down a column, all right? So as we go farther down on the periodic table, atomic radius increases. As we go to the right on the periodic table, from left to right, the atomic radius decreases. We get smaller as we go across a row on the periodic table, all right? So that is the rule. Atomic radius increases as we go down a column on the periodic table, and it decreases as we go across a row on the periodic table. So how can we explain this based on the properties of atoms that we've learned about based on their electron configurations? All right. So in order to do that, what I want to do is I want to look at the difference between a couple of different atoms. So let's say we're talking about the difference between sodium versus potassium. All right, which one is going to be bigger and why? So that should iron out the differences as we go from top to bottom in a column. And then let's talk about the difference between two atoms that are in the same row. All right, so for example, carbon versus fluorine. So when we look at the electron configurations for sodium and potassium, here's sodium on the periodic table. So sodium has the electron configuration 1s2, 2s2, 2p6, 3s1. If we're looking at potassium right underneath, very similar electron configuration, but one more shell of electrons. So potassium would have everything filled up to 4s1. All right. So if we actually look at those two pictures in terms of what they mean for the number of shells of electrons, it's pretty easy to tell why potassium is likely to be bigger than sodium. So sodium has 11 protons in its nucleus, 2 electrons in its first shell, 8 electrons in its second shell, and 1 electron in its third shell. The important thing here is just 3 shells of electrons. Potassium does have more protons, right? 19 protons in its nucleus, but it has an entire extra shell of electrons. So according to our simple definition of effective nuclear charge, there shouldn't be a difference in effective nuclear charge here. The big difference is the fact that potassium has 1 more shell of electrons altogether, right? So both of these, if you're checking your calculations for effective nuclear charge, both of them should have effective nuclear charges of +1, all right? So for sodium, 11 protons minus 10 inner shell electrons, and for potassium, 19 protons minus 18 inner shell electrons. However, the important thing, the difference between them is potassium's just got 1 more shell of electrons. So more shells of electrons normally means a bigger radius. We add more shells, the atom gets larger. All right, very simple. So that is how we rationalize what happens as we go down a column on the periodic table. We're adding more shells so the atoms get bigger. All right. Now, what about as we go left to right or right to left on the periodic table? Carbon versus fluorine. So in this case, carbon and fluorine both have exactly 2 shells of electrons. They're both in the second row, right? So second shell of electrons is the last one that gets filled. So let's look at their electron configurations really quickly. Carbon has an electron configuration of 1s2, 2s2, 2p2. And fluorine, an electron configuration of 1s2, 2s2, 2p5. Now, these are very simplistic pictures. We're not even worried about which subshell all these electrons are in. We're just counting what shell they're in to get these pictures, all right? So for carbon, we have a total of 6 protons in its nucleus, 2 electrons in its first shell, 4 electrons in its second shell. For fluorine, we have a total of 9 protons in its nucleus, 2 electrons in its first shell, 7 electrons in its second shell. So if we're calculating which one of these is bigger or smaller, how would we do that? How would we know which one of these would have a larger second shell of electrons? The important thing here is the fact that each of those shells has a different amount of pull from the nucleus on it, all right? So carbon only has 6 protons in its nucleus to pull on that outer shell on the outer shell electrons. Fluorine has 9 protons to pull on those outer shell electrons. If we're calculating the effective nuclear charge, how much pull that outer shell of electrons is feeling, for carbon, we have 6 protons minus 2 inner shell electrons, right? Only that first shell is the inner shell. The second shell is the valence or outer shell. So those protons or those electrons in the second shell for carbon have +4 worth of pull from the nucleus on them, compared to in fluorine, a +7 effective nuclear charge. So a much stronger effective pull from the nucleus on this outer shell of electrons. Well, what happens to that outer shell when there's more pull from the nucleus? The outer shell gets pulled closer to the nucleus. It gets compressed by that extra pull from the nucleus. So because of the larger effective nuclear charge in fluorine, it is actually smaller than carbon is, all right? As we add effective nuclear charge going across a row, that effective nuclear charge pulls that valence shell in closer to the nucleus. That is why as we go across a row on a periodic table from left to right, our atomic radius decreases, all right? So let's write a 1-sentence descriptor to encapsulate all that. So atomic radius increases down a column on the periodic table because more shells of electrons are added, and decreases across a row from left to right because of increasing effective nuclear charge, increasing pull from the nucleus on that outer shell of electrons. Hopefully that explanation made lots of sense, and stay tuned. We're going to talk about more of those periodic properties soon. Thanks. This is Dr. Musk.